Greetings. So, in the previous class we talked about the Ehrenfest theorem, and we get an understanding of why classical mechanics works, but we know that classical mechanics cannot be correct. There is no way you can describe the state of a system by a point in the phase space. And you need a new mathematical formalism altogether, which is the quantum theory. And then we know that it has to stand on the foundation of the principle of uncertainty, the description of a state by a state vector in a Hilbert space which evolves in time according to the Schrodinger equation. And then you can do quantum mechanics in alternative equivalent mathematical formalisms. These are alternatives, but they are completely equivalent to each other, but they have some subtle differences. And you can do quantum mechanics in what is called as the Schrodinger picture, or in the Heisenberg picture, or in the Dirac picture, which is also referred to as the interaction picture. So, we will first spend some time discussing this, and then we have already been discussing symmetries, the translational symmetry, the rotational symmetry. Then we talked about what happens when time evolves, right? And then we will today also talk about the time reversal symmetry, which is not the opposite of time evolution. So, we will discuss that. So, first thing to recognize is you have to understand that a representation is different from a picture. So, before I tell you what a picture is, you must know that it is not the same thing as a representation. You can represent the state of a quantum system in the coordinate representation or in the momentum representation. So, that is not an issue. We are going to talk about some different way of doing quantum mechanics, and these are known as the Schrodinger, Heisenberg and the Dirac pictures. This is also different from describing a state vector in an orthonormal basis set, and you can have an orthonormal basis set and you can choose any basis as long as it spans the complete Hilbert space. And then you have these rotations in the Hilbert space which are acceptable, and they are completely equivalent. So, when you talk about these three pictures, they also involve some rotations in some sense. They have similar form, but they are not the same as rotation of a basis set within a Hilbert space. Okay, so, these are different. So, these are called as generalized rotations. So, the first thing I thought I will do is to tell you what these pictures are not. So, they are not different representations, they are not different choice of basis sets. So, let us have a look at the Schrodinger equation, and the time evolution is described by this time evolution operator, which is this exponential e to the minus I h t. All right, I consider the initial state t0 to be 0, and you have the exponential operator which you can expand as a power series, and you can extract the time dependence separately, reduce it to a time independent Schrodinger equation, and when you are dealing with a stationary state, we have seen that the stationary states do depend on time, but only through a phase factor, which is e to the minus I e over h cross t, or e to the minus I omega t, right. So, these are the stationary states, and they represent the time evolution of the stationary states. This time evolution is what you called as the dynamical evolution of the system. So, this is the dynamical phase, all right, as opposed to another phase that I will introduce in the next few classes. So, this is the dynamical phase, And notice that the state functions are therefore time dependent, but the operators that you are using, the position, momentum, Hamiltonian, these are independent of time. Okay, the operators are completely independent of time. So, when you are talking about the evolution of a system, you are doing quantum theory, and quantum theory is sitting in the state vectors, it is also sitting in the operators which operate on the state vectors. But where is the time dependence? Is it in the state vector, or is it in the operators, or is it in both? So, that is a question that we are discussing now. So, now we are dealing in this representation, this particular picture that we are now using, you see that all the time dependence is contained in the state vectors, and the operators are absolutely independent of time. Okay? This is the picture which is called as the Schrodinger picture. In this picture, the state vectors or their coordinate representation is a wave function, right? And I will use the state vectors and the wave functions, you know, both the terminology I will mix it, because these are, it is just a matter of notation and you know how you represent the state of the system. The coordinate representation of a state vector is a wave function, and this wave function is time dependent, but the operators are independent of time, and this is the picture that is known as the Schrodinger picture. Now, we can do quantum mechanics by carrying out certain unitary transformations. You are doing the same physics, so there is no new concept which is being introduced, but this is different from a mere choice of basis which you can rotate and choose any basis, like a position vector in this classroom I can represent with respect to this basis, or I can choose any other basis. I can rotate this as long as it spans the full space. So, we are going to do unitary transformations which will leave the physics invariant, but it will be different from just an ordinary rotation of a basis set in the Hilbert space. So, these generalized rotations, as they are called, are effected through an operator which is O e to the I h t over h cross, right. So, that a transformed Hamiltonian in this picture has this form, the omega s is sandwiched between e to the minus I e h over h cross t and e to the plus I e h over h cross t. Okay. So, this is the unitary transformations, and we use this kind of you have seen the similar mathematics, not the same, but similar mathematics when you use a different basis set and you just rotate the basis set, right. You have exactly this type of transformations, you deal with the similarity transformations and so on. So, when you go from the operator omega s to omega h using this transformation, you are going from the Schrodinger picture to the Heisenberg picture. So, the omega h, the left hand side, carries a subscript h for the Heisenberg picture. Now, what this transformation does is that it will transform the operators according to this prescription. It will also transform the state vectors, okay, because you are doing it in a different picture. So, both the state vectors and the operators have to undergo a corresponding transformation effected through the same transformation operator. So, the wave functions in the Heisenberg picture are obtained from the wave functions in the Schrodinger picture by operating on the Schrodinger picture wave functions by the transformation operator OH, okay. And OH is e to the I h over h cross t, h is the Hamiltonian, and this is how you get the wave functions in the Heisenberg picture. So, both the wave functions and the operators in the Heisenberg picture will be different. Notice that the Schrodinger picture wave function at the time t can be obtained from the wave function at the time 0 by operating on it by the time evolution operator, which contains the Hamiltonian. But the wave function at the time 0 is the stationary eigenstate of the Hamiltonian, and therefore, the wave function at time t is the same as the wave function at time 0, except for the phase factor for the stationary states. Okay? So, this is the relation between the wave function at time t and the wave function at time 0. So, you can use this result over here, and what does it give you? It gives you that the Schrodinger picture wave function is this operator operating on this wave function, which is nothing but this phase factor times the Schrodinger picture wave function at time 0, all right. And now you can see that this is just a complex number. You can pull it out, move it to the left of the operator. This is an exponential operator involving the powers of Hamiltonian, and this will give you the corresponding powers of the eigenvalue E, because the Schrodinger picture wave function at time t equal to 0 is an eigenstate of that. And now these two will cancel and you get the Schrodinger picture wave function at time 0. What does it mean? That the Heisenberg picture wave function at time t is the same as the Schrodinger picture at time 0, which is the initial state, and that obviously is you know something, a fixed quantity that you know, and no matter what the time is, okay, now, tomorrow, day after tomorrow, it will always be the Schrodinger picture wave function at time 0. So, it is not going to change from today to tomorrow to day after, and it was the same yesterday and day before yesterday as well. Okay. So, there is no time dependence in the Heisenberg picture wave function. The system of course evolves with time, but all the time evolution is packed in the time evolution of the operator, whereas the wave functions are completely independent of time. So, this is the Heisenberg picture. It has the same physics, but in general the Heisenberg picture operators are dependent on time. But notice that if the operator that you are talking about is the Hamiltonian itself, then of course it is not a function of time. Can you think of some other operator which will not be a function of time in the Heisenberg picture operator? Any operator which commutes with the Hamiltonian, right? If you have an operator which commutes with the Hamiltonian, those observables which are simultaneously measurable, right, they will also be the same, they are not going to change. Okay? So, it is the same in both the Schrodinger picture and the Heisenberg picture, just like the Hamiltonian itself. So, this is the story we have got so far, and now that we know that the Heisenberg picture operators are time dependent, let us ask what is this time dependence. So, you take the time derivative of the Heisenberg picture operator, which is a product of these three operators, the exponential operator, then the omega in the Schrodinger picture, and then again the exponential operator, but then the phases are different. You have got a plus sign in one case and the minus sign in the other, as you see on the screen. So, you take the time derivative, and when you take the time derivative, you do it the same way as you take the time derivative of a product of two functions or three functions, it does not matter, the rule is the same. But when you are dealing with functions, it does not matter if you write the function a times the derivative of the function b, or the derivative of the function b times the function a. The order in which you write these functions does not matter. Over here it matters. because these operators may or may not commute. Okay? So, the order in which you write this, use this law of taking the derivative of a product of operators, this order has to be preserved. And in that order, you can see that the right hand side has got two terms. There would be a third term if omega was dependent on time, but in the Schrodinger picture, the operators do not depend on time, so there are only two terms. Okay? So, now the rest of it is very straightforward. So, you have got the time derivative operator operating on an exponential operator. So, that gives you I h over h cross times e to the I h over h cross t, right, and then you have the remaining terms, and then similarly here you have to take the time derivative of e to the minus I h over h cross times t. So, that is what gives you this term over here. Now, you can just rearrange these terms, because here this exponential operator has got the Hamiltonian, the first term also has got the Hamiltonian, and here also you have got the same, and the Hamiltonian of course commutes with every power of the Hamiltonian. So, it commutes with the exponential operator also involving the Hamiltonian. So, you can swap their positions and rewrite it in the form in which you now see, okay, and then extract the I over h cross as a common factor, but this h and e to the minus I h over h cross t commute, because this is a power series in Hamiltonian, and this Hamiltonian commutes with each of those terms, including the first term, which will be unity. So, you can write them any which first and the other next, right. So, once you do that, you can notice that what you have in both the terms is nothing but the same operator in the Heisenberg picture. Okay? And now you can take I over h cross as common, and you see that the time derivative of an operator in the Heisenberg picture is equal to the commutator of the Hamiltonian with that operator, multiplied of course by I over h cross. All right. So, when you get the time derivative of something, you essentially get what we are used to calling in classical mechanics as an equation of motion. So, this is the equation of motion for the Heisenberg picture operator, that its time derivative is equal to I over h cross times the commutator of this of the Hamiltonian with this operator. The Hamiltonian itself of course commutes with it, so it goes to 0, and that is the same also with every operator which commutes with the Hamiltonian, which we already knew earlier, right. So, any operator that commutes with the Hamiltonian will be independent of time. So, this is the Heisenberg equation of motion. You can take the I h cross on the other side, right, and this has got everything that is there in the Schrodinger picture quantum mechanics, and you can do whole of quantum mechanics in the using the Heisenberg equation of motion. But now you are dealing with time dependent operators and time independent wave functions. So, what have we done? We have used unitary transformations. These are generalized rotations, okay, and we have learned how to do quantum mechanics in the Schrodinger picture and also in the Heisenberg picture. But then there is a third picture which is particularly useful when you really cannot solve the problem, okay. And when you cannot solve the problem, what you always do is to solve the best approximation, okay. You sort of model that problem by something that is solvable. that I cannot solve the actual problem, but I can solve something which is similar to that problem, and therefore the solution that I have got would be somewhat similar to the solution of the actual problem. So, that is how you encourage yourself, and most of physics is really about making approximations, because you do not have exact solutions, you have to make approximations. So, you have got a problem in quantum mechanics which is not solvable, and this is where we were talking earlier about stars in quantum mechanics, and here is one of the brightest ones, Dirac. And what you do in the Dirac picture is you come to terms with the fact that, okay, the exact problem with the full Hamiltonian is not solvable, but a part of the Hamiltonian if I ignore, and if it is a minor part, then I have the other part which is the major part, which I call as the H0, that is the solvable part. You can begin with that and develop an approximation scheme. So, you leave out H1, which is what is messing up the problem. Okay? So, the culprit part of the problem is the H1. The solvable part, the friendly part, is H0. And you construct a transformation operator using the solvable Hamiltonian, because now that is the thing you can deal with. All right? So, H0 you are comfortable with, that is the friendly part of the Hamiltonian. So, you construct a transformation operator using this H0, which is the solvable part of the Hamiltonian, and then carry out transformations similar to how you did earlier in getting the Heisenberg picture. So, this is what will give you the Dirac picture, but the transformation is now effected not by the full Hamiltonian, but by the solvable part of the Hamiltonian. So, this is what is called as the interaction picture. So, the subscript is I. It is also called as the Dirac picture. So, you can use the subscript D if you like. All right. These are completely equivalent, terminology in quantum mechanics, and this is the generalized rotation again through the operator e to the I H0, and it will transform not just the operators, but as we know now, it should also transform the wave functions, and the wave function in the interaction picture will be e to the I H0 over H cross t operating on the Schrodinger picture wave function. Okay? And what this does, this transformation does, is that both the wave function and the operators in the interaction picture are time dependent. So, the system evolves with time, but the time evolution is contained completely in the wave function in the Schrodinger picture and none in the operators. In the Heisenberg picture, it is completely packed, the complete time evolution characteristic features of the system, the quantum evolution properties are packed in the operators, and there is none in the wave function. The wave functions do not change with time, they always remain what the Schrodinger picture wave function was at t equal to 0. Okay? And in the interaction picture, they both, the wave function and the operators, and quantum mechanics is about wave functions and operators. It is not in just one or the other, it is in both, and how you do mathematics with this. Okay? So, if you remember in one of our earlier discussions on quantization, I emphasized the fact that having discrete energy spectrum is not quantization, that is not the signature of quantum mechanics. You do have discrete states in some situations when you are dealing with bound state wave functions. If the wave function goes to 0 in the asymptotic region as you go far away from the potential center, then you get a discrete spectrum. Otherwise, you have a continuous spectrum as well if the wave functions are oscillatory and they do not go to 0 in the asymptotic region. So, discreteness is not the signature of quantum mechanics. The signature is dispensing with dynamical variables in classical mechanics and using operators instead of them. And what do these operators do? These operators operate on certain vectors in the Hilbert space or wave functions in the de Broglie-Schrodinger scheme of quantum mechanics. And quantization is the process of using a completely different form of mathematics as opposed to chasing a point in the phase space as you do in classical mechanics. Okay, the trajectories in the phase space give you the solutions to a classical mechanical problem, but in quantum mechanics you are looking at the time evolution of the system, and this time evolution is expressed in the quantum properties of the system, which are contained in the wave functions and the operators. And the time evolution is either in this or in that, or the other way around, or in both. So that is what these three pictures are about: the Schrodinger picture, the Heisenberg picture, and the Dirac picture or the interaction picture. So we know what stationary states are, right? And this quantum mechanics, when you do quantum mechanics with this, it gives you some results that we have not encountered earlier. Not because the earlier scheme was correct, but despite that. Okay? For example, if you have a potential barrier and you have got an incident particle represented by this red arrow which comes in and hits this barrier from the left, then there is a chance that it could be reflected or it could be transmitted. And if the energy of this particle is less than the height of the barrier, in classical mechanics you do not see any possibility at all. It is unthinkable that the particle would cross the barrier. But quantum mechanics is not governed by the trajectories in the phase space. Quantum mechanics is governed by state functions, operators, the equation of continuity that we worked with, in our previous class. And then the equation of continuity, which is required to be valid in the region of space, imposes boundary conditions at this interface. And when you impose those boundary conditions, you automatically see that the chance of this particle crossing the barrier, even if it has energy less than the height of the barrier, is non-zero. What if the particle has got an energy higher than the height of the barrier? There is still a chance that the particle could get reflected. Okay? This is again a very different type of situation which we are not used to in classical mechanics. We are used to this in our exams because even if you have the ability to pass an exam, it does not guarantee that you will, right? Because a number of things can come in your way and you may be intellectually capable of passing an exam, but then you do not. So this particle may have an energy which is greater than the height of the barrier, but it can get reflected, and a particle which has got less energy than the height of the barrier can actually cross it. So these are really shocking results, and they shock us only because we are used to thinking in terms of classical trajectories. Okay, once we abandon that idea, we come to terms with the fact that okay, measurement of position destroys information about momentum and vice versa. Then you have no choice but to abandon this picture of classical trajectories and you are using a different scheme altogether. So, you have to follow the rules of this different scheme. And what are the rules? You have got a wave function, you have got the Schrodinger equation, you have got the equation of continuity, apply the boundary conditions and see what you get, right. So, that is your educated intuition, as we would call it, and then this becomes completely intuitive, that travel past a potential barrier. So, it does not matter whether the height is less or more, the quantum results are very different from the classical results, because they are governed by the Schrodinger equation and the equation of continuity, right. For a stationary states, the divergence of the current density vector vanishes. Same thing happens in potential, in what do you call it, a quadratic potential, all right, like a mass spring oscillator or a simple harmonic oscillator. And for a simple harmonic oscillator, you have got these turning points, and if the energy of the particle is not higher than the potential energy at the turning points, the classical particle actually turns, it turns around, okay, it takes a U-turn and comes back, it stays within the well, whereas a real particle, I do not want to call it as a quantum particle, I want to call it as a real particle, which is described correctly by quantum theory and not by classical, all right. So, the real particle would have a certain probability of escaping. The classical particle does not have this possibility, there is no such possibility for the classical particle, because classical mechanics is only an approximation. The actual laws of physics are quantum. Okay, so, you have these turning points, and then they will show up in the probability amplitude, which is the wave function, or the density, which is the modulus square, right. And now that we have our basic tools of quantum mechanics, the wave functions and the operators and the mathematics of doing, so we have to develop this linear algebra. Okay. So, with this, we are now ready to use quantum mechanics to probe our objects of interest. So, there is a certain target, I want to understand what it is, right. So, I want to do an experiment with it, probe it and find out what its properties are. This is what physics is about. Okay. In Hindi, you call it as Bhautik Shastra and also as Padartha Vidyan. Okay, Padartha Vidyan is like material science. Bhautik Shastra is like studying the physical objects. This is what physics is about. So, you are exploring these physical objects, the physical universe, that is our object of interest as a physicist. That is what you will call as the target of investigation, and you need a probe to investigate it. What kind of probes would you use? You have an atom, which is the prototype of a target, right. You shine light on it, all right, and you can have the light can be absorbed. If it has sufficient energy above the ionization threshold of an electron, it can knock out the electron. You may be left with an ion in the final state and an electron in the final state, right. Or else you may have an ion in the initial state and an electron in the initial state, right, and the electron scatters against this ion or from this ion, and then in the final state again you have an ion and an electron. So, these two experiments that I am representing in this picture, they are prototype of how you investigate matter, how you investigate a target, no matter what the target is. You either shine some light on it and see how the system responds to it, or touch it, probe it, or bombard it with electrons or neutrons or positrons or some other heavy ions and see how these probe particles respond to this. So, either you use light as a probe or some other particles, either fundamental particles or complex particles, you can even fire fullerenes at them if you like, right. So, the two experiments that you have in this picture, they are prototype of a broad range of experiments that can be carried out to investigate a target. And anything, any kind of probe and interaction which you will use to investigate a physical target, a physical potential or physical object, will fall in these two categories. Either you are using electromagnetic radiation or you are using matter, and other than matter and energy, is there anything else? So, this is very comprehensive, right? It is a prototype of anything and everything that you can do to investigate a physical object, and that is the reason the techniques that I am describing here are extremely important. Okay? These are fundamental techniques. No matter what kind of experiment you are doing, you will be doing some experiment of this kind at a fundamental level. Its ultimate manifestation may be reading a multimeter, but at the bottom it is one of these things, because there is a probe which is involved, which is probing a target. So, in these two experiments you see that the final state is the same whether you come from this path or you come from this path. The final state is an electron and an ion. In every specific experiment the details will be different, but the basic formalism is what is represented by this fundamental idea. Here the initial state is an electron and an ion, whereas over here the initial state is a photon and a neutral atom. And you see that the ingredients of the reaction in the initial states are completely different. You have photon on the left and no photon on the right. You have an electron on the right and no electron on the left, right. So, the ingredients of the reactions are completely different, but the products are the same. Okay? Like making the same khichdi with different ingredients, right, but you get the same result. So, there is a certain symmetry which is involved in this, and you can expand this idea, because you see that if you have a photon and an atom, then the reaction can proceed in multiple directions, okay? And there will be a certain rate, like in kinetic chemical reactions, you have a reaction rate for a forward reaction and another reaction rate for a backward reaction, right. So, the reactions may proceed either forward or backward, either from left to right or from top to bottom or from left to top or any which way, right. And you may have either photoionization experiments, you may have electron ion scattering experiments and so on, but the physics is really the same. It's the same machinery, the same physics, which is why quantum collision physicists, photoionization physicists, they are all using the same quantum mechanics. So, there is a certain symmetry which is involved in these processes, which is what preserves the same physics, but you have to study this carefully because the solutions depend on boundary conditions. Okay, what are the boundary conditions that you impose, and in each experiment the boundary conditions are different. So, here is an experiment. So, if you just look at this part, so this is the operator for what I will be calling as the time reversal operator. So, I will come to that in a moment. For the time being, just focus on this part of the picture, that you have got an incident plane wave, which is a beam of electrons which is scattered against a target, and then the scattered particles could be dispersed after scattering in different directions. The probability that they go toward north or south may be different, right. There may be anisotropies involved in it, but generally they have the possibility of spreading out in a collision experiment. What happens in a photoionization experiment? A photon is absorbed by the atom. This is the Einstein photoelectric effect. A photon is absorbed and an electron is kicked out. So, this electron which is kicked out, it goes as a free electron. So, it goes as a plane wave, and once it picks its direction, it is not going to go in any other direction. Okay? The chance that it may pick toward left or right may be different, but once it happens in the final state, the exit channel is unique, whereas in the collision experiment it is the entrance channel which is unique. All right. In photoionization, it is the exit channel which is unique. What about the entrance channel? There was no electron in the initial state at all. It was born when the photoionization actually took place, right. So, there was no electron to begin with, and you can simulate this no electron by having a spherical ingoing wave, so that the flux coming from this direction cancels the flux going from this direction, and there is no net flux, which represents the no electron in the initial state. Okay. So, you have got ingoing spherical waves in photoionization, whereas in collisions you have got outgoing spherical waves. All right. So, these are the boundary conditions that you must use, and if you look at these pictures, you will appreciate the term that motion is reversed, and the way to go from the collision to the photoionization is through this reversal of motion. So, if you come up with a motion reversal operator, then the solutions of the collision quantum mechanics will be applicable in photoionization physics. Okay? And this motion reversal is usually called as the time reversal. So, this symmetry is called as the time reversal symmetry in quantum mechanics. All right. Actually, Wigner, I believe, would have preferred the term motion reversal rather than time reversal, but time reversal has come into play and it has got stuck. But what it really implies is motion reversal. Okay. So, in a one dimensional case, you have this kind of a situation that you have got a particle which is incident, it can be backscattered or it can penetrate, and in photoionization you do not have anything to come in at all. So, you are represented by dotted arrows which cancel each other, whose flux cancels each other, but then you do have a particle exit channel is unique in this case, right. So, this is the meaning of time reversal symmetry, and one must recognize that the time reversal symmetry is different from t going to minus t. So, here in quantum mechanics you have to work with the Schrodinger equation, all right, because you are no longer dealing with trajectories. So, let us take the Schrodinger equation, which is what I have written here. Let t go to minus t. So, every t is replaced by minus t, and the equation that you see in front of you now, by replacing t going to minus t, is no longer the Schrodinger equation. This is not the Schrodinger equation, right. The Schrodinger equation has got a particular structure. It has got certain signs. You cannot change these signs arbitrarily. You can't change the complex conjugation arbitrarily. Okay? Each term, each sign, what is I h cross cannot be written as 1 over I times h cross, right. So, I has to be there in the numerator here. However, now that we know that this is not the Schrodinger equation, if you let t go to minus t and also do a complex conjugation, so that in place of I you get minus I, and in place of minus I you get I plus I, and in place of psi you get psi star. V does not change because V is a real potential, it is a real physical potential, right. Then you see that you have recovered the Schrodinger equation. Okay. So, in quantum mechanics, t going to minus t and psi going to psi stars, the complex conjugation must go hand in hand, and psi going to psi star has got no classical analog. In classical mechanics, t going to minus t gives you symmetric equations of motion. Look at F equal to ma. Okay. You have got the second derivative of the position vector, and the second derivative has got d2 by dt2, t goes to minus t twice because you are taking the second derivative, and the minus 1 cancels the minus 1. You look at the Hamilton's equations. Okay. You have two first order equations, but they are not symmetric in sign, so that takes care of it. So, the classical equations of motion, whether the Lagrange or the Newton or Hamilton, they are all completely equivalent, and they are all symmetric with respect to time reversal, t going to minus t, which is why given the conditions at t at a certain time, you can predict where the moon will be tomorrow, but you can also figure out where it was yesterday, because the equation of motion is symmetric under time reversal in classical mechanics, right. So, these symmetries were studied very extensively by another star, Eugene Wigner, who we see contributing to such a vast canvas of quantum mechanics, atomic physics, and other applications in even nuclear and particle physics. So, he got the 1963 Nobel Prize, and that brings us to the consideration of the role of symmetries in quantum mechanics. So, you have got the translational symmetries in some situations. In crystals you have translational symmetries, in single atoms you have rotational symmetries, you have the SO3 symmetry, you have got the dynamical symmetries in some situations, which expands the SO3 group to SO4. So, I will probably talk about this in some other class later, or refer you to some other lectures which I have given as part of a different course, but they are available to you. So, you have different symmetries. You have the translational symmetries, the generator for translation being the momentum operator. You have the rotational symmetry, the generator for which is the angular momentum operator, and we studied the algebra of the rotational operators and also the translational displacement operators, right. One is abelian, the rotations are non-abelian, so we discussed that. And in general, you have a symmetry operator which is represented by 1 minus I over h cross epsilon g. So, this is the form of a general symmetry operator, as you can see. Both the translational displacement and the rotational displacement have exactly the same form. So, this is the general character of a symmetry operator, and this symmetry operator commutes with the Hamiltonian, which is why it is a symmetry operator. The reason it is a symmetry operator is because it leaves the Hamiltonian invariant, and this invariance is the symmetry that you are really talking about. So, there are in the rotational symmetry, there is a continuous symmetry that you are talking about, because you can carry out these rotations through infinitesimal angles, okay? And you can vary these angles through infinitesimal angles infinite times. So, this is a continuous operation, okay? As opposed to this, there are discrete symmetries like parity. You have got a mirror, you have got an object here, you see the image is similar to this object, but this is a one shot single step symmetry. It is not like rotation that you can go around this axis through infinitesimal angles. Infinite number of infinitesimal angles is what will take you around this axis, but a single step jump from the real space to the image space, this is parity. Okay? So, this is the discrete symmetry. It is symmetry because yes, what you look in the image is similar to this, right. So, it is a symmetry. Of course, there are certain differences, the left goes to right, right goes to left and so on, or top to the bottom and bottom to the top, right. So, that is a matter of detail. It depends on what kind of orthogonal transformation it is, does its determinant, is it positive or negative and so on. So, these are the details which will go into the understanding of these different symmetries. There are other discrete symmetries. So, parity, which is reflection from here to here, parity or inversion is a discrete symmetry. Time reversal is a discrete symmetry. You go from time t to minus t. You do not go through the intermediate times. That is not what time reversal is. It is a discrete symmetry. In classical mechanics, there is nothing more than t going to minus t, whereas in quantum mechanics t goes to minus t, but psi also goes to psi star. And then there is another discrete symmetry, which is the charge conjugation. The electron goes to positron, right. Everything remains the same, but the charge has jumped from plus to minus and vice versa. So, that is again a discrete symmetry, okay. And the PCT theorem is about these discrete symmetries, which is the parity, charge conjugation and time reversal. So, these three together give you this Lorentz group and the standard model of physics. So, in classical mechanics, if you come to the present from the past and the particle has come along a certain trajectory, you have the time reversal symmetry, because as I explained, the classical equations of motion are symmetric under time reversal. You will follow exactly the same trajectory in classical mechanics by reversing the momentum at t equal to 0. Okay. So, this is the picture in classical mechanics. If you just reverse the momentum, you will recover the history of that particle. And it is the same whether you solve the equation of motion using Lagrange, Newton or Hamilton formulation, right. So, classical trajectories are completely reversible, and in quantum mechanics, time reversal symmetry has to be handled with care, which involves different boundary conditions. You need the complex conjugation to accompany t going to minus t, they go hand in hand, right. And you are now dealing with dynamical variables, position and momentum. There is also an uncertainty between energy and time, which are also canonically conjugate in the classical sense. Okay, these are canonically conjugate variables. So, if you read Goldstein's book, you will know that okay, these are canonically conjugate variables, right. However, although these two uncertainty principles look so similar, they are fundamentally different, because the equation for Q and P we got, if you remember in the previous part of the course, we arrived at this from the generalized uncertainty principle, Schwarz's inequality and so on. So, you remember that analysis? That is how we arrived at the uncertainty between position and momentum, by taking the root mean square of the expectation values of the operator square, its difference with the square of the expectation value of the operator and so on. So, that is the analysis I want you to bring back to your mind when thinking about the relation delta q delta p greater than or equal to h cross over 2. Now, this relation looks exactly the same, but there is no operator for time. There is no operator for time. So, in the initial years of quantum mechanics in the 1930s, there were some attempts to introduce an operator for time. The energy spectrum of the Hamiltonian for a bound state, it is bounded, all right, but for time you do not have any such lower bound, and there are intrinsic difficulties in introducing an operator for time. So, this uncertainty principle is valid, but there is a different reason for it. It comes as a consequence of the previous one rather than as a fundamental uncertainty between conjugate operators. There is no operator for time. So, time is used only as a parameter in quantum mechanics. There is no Hermitian operator for which you can find an eigenvalue. So, Wigner in 1932 referred to this as reversal of motion rather than as time reversal. Okay? And you must now see that the time reversal operator is not the inverse of the time evolution operator. Okay? The time evolution operator is what we have discussed, and that is the one which goes into the Schrodinger equation. So, do not let the colloquial meaning of time evolution and time reversal confuse you. The time reversal operator is a well defined operator in quantum mechanics. It has to be understood in the context of quantum mechanics and understood in how it is defined in quantum mechanics, all right. And how it is defined in quantum mechanics would be this, that if you think of a state vector which evolves with time, then this is the relation that you have in your mind, that you have got a state vector, the time evolution operator operates on it, and you get the time evolved state, which is the left hand side of this equation. Okay? If you have a time reversal operator, whatever it means, okay, when that operator operates on a state, arbitrary state alpha, you will get what you can call as the time reverse state, right. And if you now look at the time evolution of the time reverse state, so you first operate by the time reversal operator, which is represented by the operator theta over here, and operate on this by the time evolution operator, you have the time evolution of a time reverse state, and you can also have the time reversal of a time evolved state. And what we have in our mind to develop quantum mechanics is that we certainly expect that the time evolution of a time reversed state must be the same as the time reversed of a time evolved state. That is what we expect. And this relationship is going to guide us to discover the form of the time reversal operator. The time reversal operator theta must be such an operator which guarantees that the time reversed time evolved state is the same as the time evolved time reversed state, right. This is the guiding principle which will determine the form of the time reversal operator. So, this is our expectation, right. So, we will see what is the condition on the time reversal operator, what should be its property so that this relation remains valid. So, consider an arbitrary state, consider a certain transformation theta. We will talk about time reversal operators in general, but specifically let us think about any operator theta, and you get a new state which is alpha tilde, and from a state beta you get the beta tilde, right. And theta is an antilinear operator if it operates on scaled vectors, vectors scaled by some complex numbers, and then gives you a linear superposition but with complex conjugate coefficients, which is why they are called as antilinear operator, okay? Because you can extract the coefficients, but when they come out as complex conjugates. For linear operators, they come out just the way they are. So, this is an antilinear operator. Now, if an operator is antilinear, and in addition to that, if you take the inner product beta alpha, it is the complex conjugate beta tilde alpha tilde. If it is the complex conjugate of beta alpha, right, then it is called as anti-unitary. So, these are the definitions of an antilinear and an anti-unitary operator. So, now let us look at this relation, which is our guiding principle, and if this relation is to be valid, then you just multiply throughout, you get the next step which you see on the screen, right. You cancel the thetas on both sides, you cancel the minus sign on both sides, okay. Do it carefully, one step at a time. Cancel the theta, cancel the minus sign. What else can you do? Cancel the delta t, all right. That is the time interval. And then you are left with a minus sign on the right side and a different order of h and theta, okay, and a different position of I. So, you have IH theta on the left and minus theta IH on the right, and whether I on the right side of the equation can be moved behind the theta with a plus sign or minus sign depends on whether theta is unitary or anti-unitary, okay, because anti-unitary will reverse the sign, will make it complex conjugate. So, plus I will become minus I. So, you have to be careful with this. If theta is a linear operator, if, not that it is, but if, just for the sake of discussion, we presume that theta is a linear operator, then theta I would be the same as I theta. And what would it give us for the right hand side? It would give us minus I theta h, and this would give IH theta equal to theta h, or essentially we would get, if you operate on an arbitrary eigenstate of the Hamiltonian, which is an energy eigenstate, then you would get h theta giving you minus En operating on h theta En equal to minus En theta En, as you can see from this relation. It is very straightforward. Now, this would make no sense if the energy states are eigenstates of a free particle, for example, and a free particle has got only positive energies. So, how do you put negative energies in your algebra, right? So, this cannot work, which means that theta cannot be a linear operator, it is actually an antilinear operator. Theta must not be a linear operator. So, that is the conclusion that you draw, and then you make the other choice, which is that it is an antilinear operator, and this choice gives you no inconsistency, all right, because then it takes care of the sign properly. So, you do not run into any paradoxical situation, all right. So, you get the time reversed state is also an eigenstate of the Hamiltonian belonging to the same eigenvalue, and there is no conflict with common sense so far as this situation is concerned, right. So, this is an anti-unitary operator, and this is what is involved in psi going to psi star. I mentioned that t going to minus t has to be accompanied by the wave function becoming complex conjugate, right. And then there are other properties of the time reversal operator, which I will let you work out as homework. You can see that the position operator remains invariant. The momentum operator, however, picks up a minus sign, right. So, these are some of the properties. You can see what the time reversal operator does to the position operator, what does it do to the momentum operator, what does it do to the angular momentum operator, right. Does it commute with it, does it anti-commute? So, these are simple problems that you can work out at home, all right. So, these are the properties of the time reversal operator, which you have the parity also, which is again, like I mentioned, a one step discrete symmetry, and this is what quantum mechanics is really about. So, you have to use the very robust structure of the algebra of quantum mechanics. So, it is a set of rules, okay, and they describe nature accurately. The reason quantum mechanics is accepted as the correct theory of nature is because no experiment has ever been done anywhere which violates anything that quantum mechanics predicts. There are some problems when you deal with relativity and so on, so I will not get into that, but barring that, this works. Thank you.